We already know that integration in one dimension amounts to finding the area under the graph of a function. Since we can graph multivariate functions, we want to do the same thing with them. But we note that while in one dimension our domains were always intervals, in multiple dimensions they could really be any shape. So there are some additional challenges that we're going to have to face in tackling these types of integrals. We'll start then by generalizing the notion of an interval to multiple dimensions. Such things are, perhaps unsurprisingly, called rectangles. A rectangle in Rn is any set which is the product of closed intervals, like so. If we write this in set builder notation, it's the collection of n tuples such that xi lives between ai and bi. To see why these are called rectangles, let's try drawing one, like the rectangle 1, 3 cross 2, 4, which is a rectangle in R2. Plotting this set in the Cartesian plane, we're looking at the collection of all points such that x is between 1 and 3, and y is between 2 and 4. The thing we get will indeed be a rectangle, and in higher dimensions is the appropriate generalization of a rectangle. With our simple domains in place, we can now define the integral itself. If f is a function of n variables, and r is a rectangle, then the integral of f over r is the signed area under the graph of f, and is denoted as follows. There are n integral signs here to remind us that we are integrating in Rn, while the dv term should be thought of as telling us that we're finding a volume. Okay, so how do we actually compute this? Just like with partial derivatives, we couldn't handle every variable simultaneously. We handled one variable at a time, and in doing so pretended that all of the other variables were constant. And that's effectively what we're going to do here. We will integrate one variable at a time, treating all the other variables as constants. More concretely, let's let R be a rectangle of the following form, in which case the integral over f can be evaluated as an iterated integral, like so. That is, we're going to break this integral down into n one-dimensional integrals, and integrate each variable one at a time. And very importantly, note that the bounds of integration exactly match the order of integration. So when we integrate dx sub n, we use the bounds for x sub n, while when we integrate x sub 1, we use the bounds for x sub 1. Let's put this to work with an example and find the area under the graph of x squared y plus yx squared on the interval 1, 3 cross -1, 1. Setting this up as an iterated integral, we get the following, which consists of two integrals, one over the interval 1, 3, and the other over the interval -1, 1. Or, if it helps you to see what's happening, we could instead write it like this. We'll evaluate the inner integral first, which is with respect to dy. This means that we're treating x as a constant. Integrating the y terms then gives us this. And in writing the bounds of integration, I like to write y equals -1 to 1, just to remind me which variable I'm subbing into. It's not at all necessary, but I find that it helps. So we'll plug in -1 and 1, for which there's a lot of cancellation and simplification we can do, resulting in 2/3 x. So we finish up our last integral, getting an answer of 8/3. Now you could have solved this by integrating in the other direction, namely letting x be the inner integral and y be the outer. If you do this though, don't forget to change the order of the bounds as well. So, as long as we're integrating on a rectangle, we can solve multivariate integrals by splitting them up into integrals over each of their components.